Here's our first sample problem for this topic about pumps. This problem is taken from the review text by Bautista, Fundamentals of Pumps, Fans, Blowers, and Compressors. The problem says that water from a well is to be pumped to a height of 40 meters from the source. The quantity of water to be delivered is 500 liters per second through a 480 diameter pipe. It is also desired to maintain a 100 kilopascals pressure at the summit, and the frictional losses from the suction and discharge of the pump are equivalent to 2.0 meters. If the pump speed is 850 RPM, determine the power needed by the pump in HP. Right, so here's our figure. We have here a well at this lower side, and at the higher side we have this pressurized tank. And we want to transport the water from this point to that point. Right, so here's our pump, and the distance from the center line to this, that's actually 40 meters. Actually, it's not. It should be up to this point. Right, so it should be up to this point. That's 40 meters. So from here to here, that's 40 meters. Okay, and take note that this one is pressurized, so that means this is 100 kPa. This one is exposed to atmospheric pressure, and that means that the pressure is zero at this point. Right, so what we want, or the point under consideration, is from this point to that point. Okay, and it says that the frictional losses from the suction and discharge of the pump are equivalent to 2.0 meters. That means that the frictional losses from this suction line, the entire suction line to the entire discharge line, is equivalent to 2.0 meters. So if the pump speed is 850 RPM, determine the power needed by the pump in HP. Right, so the question now is, are we looking for the brake horsepower, the water horsepower, or the motor input power? Now, since we don't have efficiency, then of course we can assume that the power required right here is just the water horsepower. Right, so to do that, we know that the water horsepower, the equation for that is just simply the flow rate times the unit weight of fluid times the total head. So therefore, our first step would be to solve for the total head. Right, so solve for the total head. Right, so recall that the total head, HT, is just equal to the total static head, which is just simply the pressure head, HP, plus the elevation head, plus the dynamic head, total dynamic head, which is equal to the velocity head plus the losses, plus HL. Right, so for the pressure head, let's solve this individually. So P sub 2 minus P sub 1, and take note that the point under consideration is this point and that point. So here's our point 1, and here's our point 2. Right, so P sub 2 minus P sub 1 by divided by this unit weight. This is 100 kPa, so 100 minus 0 divided by the unit weight of water, which is just 9.81. Since this is kilopascals, then we'll use this kilonewton per meter cube. 9.81 kilonewton per meter cube. This one is kilonewton per meter squared, because that's kilopascal. And this is, so 100 divided by 9.81. This is 10.2 meters. It's 10.2 meters. Right, so next is the solve for this elevation head. That elevation head is just simply from this point to that point, and that's already given. This is 40 meters. So 40 meters. Right, so next one is the solve for the velocity head. H sub v is equal to v2 squared minus v1 squared all over 2g. Right, so v2 squared, that's the velocity right here, and that velocity is, since we have this flow rate, and we also have the diameter of the pipe, so that means we can solve for the velocity. Q is equal to AV, right? And for the velocity at point 1, so recall that whenever we have a large reservoir, okay, so take note of the word large reservoir, and if we are, or if our point of reference is the surface, that means that we assume that the velocity right here is actually 0. So that's the always assumption that we do for a large reservoir, and if our point under consideration is the surface, right? So we know that, I mean, of course, in reality, it's not 0 because it's decreasing if it's being pumped, but uh, the decrease is actually negligible because it's just the supply is just too large that we could notice a significant decrease in the height right here. So the velocity right here is 0. So solve first for v sub 2. So we know that v sub 2 is just equal to q all over a, and our q is 500 liters per second. 500 liters per second. So convert this to cubic meter. This is 1000 liters per 1 cubic meter divided by pi d squared. So 0.48 squared all over 4. So v sub 2 is equal to 500 divided by 1000 divided by pi over 4 times 0.48 squared. So we have 2.76 meters per second. 2.76 meters per second. Right, so if we substitute this to that equation, what we get is 2.76 squared divided by 2 times 9.81, since this is 0. So squared divided by 2 times 9.81. We have 0.39 meters. And for our head loss, that's already given 2 meters. Therefore, H total is equal to HP, which is 10.2, right? 10.2 plus the elevation head plus 40. What else? Plus the total dynamic head of 0.39 plus 2 meters. So we have 52.6. So this is 52.6 meters. So now that we have this total head, then therefore we can solve for, so we can now solve for the water HP, or water power. So WP is equal to the flow rate times the unit weight of water times the total head. The flow rate is 500 liters per second, or 0.5 cubic meters per second. The unit weight is 9.8 kilonewtons, 9.881 kilonewtons per cubic meter. That's the unit weight of water, and times the head of 52.6. So 52.6 times 9.81 times zero point 0.5. So we have 258 kilowatts. This is 258 kilowatts. So we need to convert this into HP. So um, so the water power is 258 kilowatts times the conversion of 1 HP is equal to 0.746 kilowatts. And what we get here, 346 HP. Okay, so if we do a recap on what we did, so first we solve for the total head, and we write the general equation including the pressure head, the elevation head, plus the total dynamic head, the velocity head, plus the head losses. So what we did was to solve first for the individual head terms. So P sub 2 minus P sub 1. The P sub 2 is 100 is because it is pressurized. As compared to this is exposed to atmospheric pressure, and therefore there is the pressure, the gauge pressure there would be 0 because that's the reference pressure value. And for the elevation head, is just simply the distance from this point to that point. So distance between 2 points considered, our point 1 and point 2. And for the velocity head, we need the velocity at each point. But for point 1, the velocity, if it's a large reservoir, the assumption always is that the velocity there is 0. But right here, the velocity is, we have a value of velocity here, and we can obtain that through the use of the flow rate equation. Q is equal to VA. Since we have Q, we have A, then we can solve for the velocity. Okay, so next one is we have the head loss term. It's already given, and therefore we can solve for the total head for the pump. And since we have the total head of the pump, then we can solve for the water power, which is simply Q times this gamma times H. And we convert this kilowatts into horsepower. Okay, so that's it. Then next sample problem is this one. So the next sample problem is still taken from the reviewer text by Bautista. The problem says a water source with an elevation of 10 meters is to be pumped by a centrifugal pump to an open reservoir at an elevation of 8 meters. The suction pipe and discharge pipe diameter is 225 mm and 200 mm respectively. The pump center line is 5 meters. So the pump center line is at 5 meters, and the head loss at suction pipe is 0.05 meters and 0.45 at the discharge pipe. The pump delivers water at 15 liters per second and has an efficiency of 75%, while the electric motor is 80%. Determine the water HP, the brake horsepower, and the power input to drive the motor, and also the pressure gauge readings installed before and after the suction and discharge of pump in kilopascals. So here's our illustration for the problem. Here's our suction side, here's our pump, and here's our discharge side. So we have this reservoir, let's say at point A, and let's say here at point B. And we have a installed a pressure readings right here at, let's say this is pressure 1 and this is pressure 2. So take note, for now we'll use the subscript, let's say A and B for this level. Okay, so I think this should be 80 meters. Just take note, this must be 80 meters because we have 10 plus 70, so that's gonna be 80 meters. And I think this must be 5 meters because from the source or from a reference datum, this is 10 meters. Okay, so again, a water source with an elevation of 10 meters. So that means if here's our reference datum, so from this reference line to this one, that's the elevation of 10 meters is to be pumped by a centrifugal pump to an open reservoir at elevation of 80 meters. So that means from this to that, that's 80 meters. And the suction and discharge pipe diameter is 225 and 200 mm respectively. So here's D1, that's the suction side, and here's the discharge side. We have the diameter given. And what else? The pump center line is 5 meters. So that means again from this reference point to the center line of the pump, that's 5 meters. The head loss at suction pipe is 0.05 and 0.45 at the discharge pipe. So you have the head loss in the suction side, which is different from the head loss at the discharge side. And the pump delivers water at 15 liters per second and has an efficiency of 75%, while the electric motor is 80%. Okay, so first thing that we do is to solve for the total pump head. So once we have the total pump head, then we can solve for the water horsepower. And if we have the water horsepower, since we have the efficiency, then we can solve for the brake horsepower. And since we also have another efficiency for the motor, then we can solve for the power input to drive the motor. Right, so let's do that. So for the solution, so first is solve for the individual head terms. Right, so recall that our total head is just simply the pressure head plus the elevation head plus the velocity head plus the head loss. And take note that this is what we term as total static head, and this is what we term as the total dynamic head. Right, so HP, the pressure head, is actually let's, even though it's just 0, P sub 2 minus P sub 1. So this is atmospheric pressure. This is also atmospheric pressure. This will be 0, right? Our H sub Z is, okay, so we want to elevate the water from this source or from this line up to this line. So it's not just right here at the end of the discharge pipe, but rather up to here, because there's going to be a head or additional head from this point to that point, right? So that's going to be 70. So H sub Z is 70 meters. For the H sub V, this is V2 squared plus V1 squared all over 2G, right? So from this point, here's our point A, and here's our point B. So that means that since it's a large reservoir, then we can just simply assume, since this is 0 plus 0 squared, so it's just 0. And for the head loss, we have head loss from the suction side, which is equal to 0.05 0.05 plus the head loss at the discharge side 0.45. So this is 0.5 meters. And therefore, the total head is the total pump head is, so HT is equal to 70 plus, right, plus 0 plus 0 plus 0 plus 0.5. This is therefore 70.5 meters. Okay, so next is, let's solve for the brake horsepower. Right, so recall that the brake horsepower is related to the water power by this efficiency. So water power divided by BHP. Therefore, BHP is equal to water power. Oh, I think we still have to solve for the water power. Anyway, we can just write it here. Or it's good to have a separate line for that. So solve for water power. So water power is equal to Q times times this, times the height, total head. Our Q is 15 liters per second. And let's convert this to cubic meter. We have 1,000 liters times the unit weight of water. Since we are in metric units, this is 9.81 kilonewton per cubic meter times the head of 70.5 meters. So 15 divided by 1000 times 9.81 times 70.5. So this is 10.37 kilowatts, and convert this to horsepower. This is 0.746, 1 HP. This is 1 kilowatts. So divided by 0.746, this is 13.9 HP. Right, so now since we have that, then we can solve for what's this? Brake horsepower. So brake horsepower is related to water horsepower by the efficiency. So we have your water power divided by brake horsepower. Therefore, brake horsepower is equal to water power divided by the efficiency. So let's use this horsepower value 13.9 divided by the efficiency. The efficiency, it says that we have a 75% efficiency, or 0.75, and that means 13.9 divided by 0.75. This is 18.54. This is 18.54 HP. And since we now have the brake horsepower, then we can solve for motor input power. So how do we do that? It's just simply brake horsepower divided by the motor input. So, or let us write it here. So this is, let's say, pump, and this is motor efficiency. So brake horsepower divided by the motor input. So let's just write P input, or horsepower input. And this is 18.54 divided by 0.8. So divided by 0.8, this is 23.2 HP. Okay, so we're done, and let's go to, or we still have to solve for this. The pressure gauge readings, determine the pressure gauge readings installed before and after the suction and discharge of pump. Right, so To solve that, to solve for the pressure reading at P1, then we need to apply the Bernoulli's equation. So if we draw it here, right? So here it is, and here's our point. Let's say here's our point A, and here's our point 1. Or since we use point 1 right here, anyway, let's just write point 3. No problem. And here's gonna be point 1. So we need to apply the Bernoulli's equation, or the energy equation rather, to this side right here. We need to apply the energy equation at at point 1 and point 3. Okay, so let's do that. So P1, so take note, this is point 1, this is point 3. So P1, so P1 by rho, by this unit weight plus V1 squared all over 2G plus Z sub 1 is equal to P sub 2 by unit weight plus V sub 2 squared all over 2G plus Z sub 2 plus the head loss. Right, so energy in is equal to energy out. So the energy input is just simply the energy of this, the hydraulic energy of this fluid, is just simply the pressure head, velocity head, um, and the elevation head. So we don't have the horsepower, the head for the pump, because we are only considering just before this pump. So therefore, there is no pump in this right here. So here's our system considered only. Right, so that means there's no pump terms, and of course we need this elevation. This is 5 meters, because from the reference datum this is 5 to the center line, and then up to this water level, that's still 5, so 10 meters. So that's why right here we have 5 meters. And since we have the head loss, it says here that head loss is equal to HL is equal to 0.05 at the suction pipe. So therefore this is, alright, so the pressure is, this must be 3, this must be 3 as well, and 3. So the pressure at A, since it is atmospheric pressure, this is 0. And the velocity right here, since it's a large reservoir, then this is also 0. The elevation is, if this is our reference point, that's gonna be 5 meters, right? So 5 is equal to P sub 3. Actually there is a pressure here, so that's why there is a value, and that's what actually we are solving for. So divided by 9.81 kilonewton per meter cube, and this is meters, plus the velocity right here. If we solve this, Q is equal to AV, and V at this point is equal to Q all over A, and the Q is 15 liters, or 0.5 cubic meters per second, divided by pi. We have this diameter, this is 255 millimeters, So pi times d, 0.255 squared all over 4, and this is so 0.255 squared times divided by 4, and zero point 0.5 divided by answer. This is 9.8. So this is 9.8 meters per second. Right, so this is 9.8 meters per second squared divided by 2 times 9.81 meters per second squared. So take note that this 9.81 is the acceleration due to gravity, whereas this 9.81 is the unit weight of water, which is the product of density times the gravity, acceleration due to gravity. So if the water density is 1000, so 1000 times 9.81, you divide that by 1000 again because we are in this kilonewton prefix, so that means we have this value. Right, so I guess we'll continue this discussion in the next video.